This is video 17A about viscoelastic materials. We've now finished the first 2 units of statics, and this is the first topic of the unit on biomaterials properties, that is, on how the molecular structure of a material determines the mechanical and biological responses to stress. And in this unit, we think about more complicated properties than can be described by Hooke's law. So first we have a definition of viscoelastic materials. This kind of material is part viscous and part elastic. The elastic part causes it to depend on the strain in the material, and the viscous part causes it to respond to the rate of change in the strain, as a fluid would respond to your rate of movement of the fluid. So because of this, the stress-strain relationship is history or time-dependent, as you see in this graph, where the stress as a function of strain is different as we stretch the material than as we relax it. We use differential equations to describe viscoelastic materials because they're dependent on rates of change, which means time derivatives. And in this unit, we'll only address linear elasticity, meaning that the stress is proportional to the strain at equilibrium. That means when the derivatives are zero. Of course, when the derivatives are non-zero, when the material is still moving, we don't see a linear stress-strain relationship, as we see in this graph. Viscoelastic materials create characteristic behaviors in different tests. One of these is the creep test, and in the creep test we step the stress up from 0 to some designated amount at time 0, and then we record the strain, and what we see is the strain creeps upward as over time it can adapt to that stress that was applied. A stress relaxation test is one where the strain steps up from 0 to some defined strain we call here epsilon naught, and we record the stress, and what we see is that the stress will relax downward as it adapts. A hysteresis test is any test in which we first increase or decrease stress. The stress may be changing linearly as we increase and decrease it, or may be a sinusoidal response that cyclically increases it and decreases it. Either way, what we see with hysteresis is its plot. Instead of against time, it's usually plot as stress over strain, and that's where we see these different curves, and the region inside is energy that's lost to heat. So viscoelastic materials arise from a number of different molecular bases. A common type or cause of viscoelasticity is hydrogels that have water between fibers. So in these, there are fibers that move around as the material stretches, and as they move, the water has to reorganize because water only deforms by the molecules moving relative to each other, and at very small levels, there's fairly high viscosity for water to move when it's so constrained. We see examples of hydrogels are most biological tissues, with the possible exception of bone, which is primarily elastic, although has some viscoelasticity. Tissue scaffolds that are created in a lab for tissue engineering, blood clots that develop in the body, and other things. Viscoelasticity can also arise when the fibers in the material themselves take a while to change under force. Maybe they have proteins that fold or unfold, and these occur, but not instantly in response to force. Again, tissues, blood clots, and muscles contracting and expanding involve protein fibers that can change. This week we'll use mathematical models of viscoelastic materials in order to describe their behavior. We'll first learn how to model material behavior, and this will be used, the goal of this is to predict the material properties, but because we're not predicting the geometry per se, our models are in stress and strain, not force and distance. That is, we're understanding material behavior, not the behavior of an object. Well, to do this, we'll incorporate viscous elements and elastic elements and even stress-producing elements like muscle. And then we'll build linear differential equation models where the model represents the material behavior and initial conditions, and pushing functions will reflect the condition the material is subjected to. And together, this allows us then to take the description of the problem to create a model and to define the test. These together create an ordinary differential equation with initial conditions, and by solving these, we will get the outcome. And specifically, we will use Laplace transforms to solve these equations. So the learning objectives of this model include predicting the behavior of the viscoelastic materials, learning to build the models, ordinary differential equation models for engineering problems. This tool can carry on into future quarters, even on other problems that are not mechanics. And then, of course, to solve these differential equations using Laplace transforms, which is a very powerful tool. Because this is a learning objective of this week, you have to use Laplace transforms to solve these problems, even when you could solve it faster another way. Initially, we'll often do ones that could be solved faster a different way in order just to build skills in this method and to be able to easily compare it to the answer you could get elsewhere.